and get right into it. So we are recording here. We are in section now, chapter 5, section 5.1. 5.1 deals with integrals. And what we're going to be attempting to do is find the area underneath a curve. Okay, that's what an integral, a definite integral is. And you'll see that integrals ultimately will relate to the antiderivatives that you just learned about. Finding the area underneath a curve from one point to another point is actually related to antiderivatives. So, but we have to, we're introducing this. This is new to you. I mean, you all know how to find the area of a square and a triangle, but you're going to be able to find the areas underneath curves of a lot. Well, I guess I don't want to get too complicated here. So you're going to be finding areas underneath curves is a very important topic in calculus. And that's what we're going to learn here in chapter 5. So let me give you a moment to copy this example down. Okay, all right, class. So we'll take a look at this. One more moment. Okay, so all right, let's take a look at this problem. What we're gonna do is we're gonna use 4 rectangles to estimate the area underneath the graph of a function, and our function is f of x equals 2x squared, from x equals 0 to x equals 1 using the following approximations. And of course, when you see the pictures, these approximations are going to be more and more clear. But R sub 4 is when you have sample points that are right endpoints. L sub 4 is when your sample points are left endpoints. And M sub 4 is when sample points are midpoints. And of course, none of this makes a lot of sense now until you see some pictures, which you will. And then we're being asked which of the above estimates are overestimates, which are underestimates. Okay, so what I'd like to do, I hope I've given you enough time here, may I go to the next page where we can, look at the solution? Does everybody have this copied down okay? Okay, but Sue is good. Good. John's good. Wonderful. All right. Well, all right. So let me show you what we're doing here. All right. Here we go to the solution. Okay. And this graph on the left is for part A. This graph on the right is for part C. But let me show you what we're doing here. And again, the book has similar pictures, but I'm just trying to, keep things very simple. And I know it's going to take you a little time to copy stuff down. But let me just talk about this graph here that you see. So what I've done is I drew the function f of x equals 2x squared. Okay, I drew it right here. Okay, there it is. And what I want to do is I want to estimate the area underneath the curve. So this is the area that I want to estimate. I want to estimate all the area underneath the curve f of x equals 2x squared and above the x-axis. I want to find out what that blue area is. But you see, since the area under the function 2x squared, under that parabola, that's not the area of a triangle. That's not the area of a square or a trapezoid. It's not an area that I have a formula for. For you all, this would be the first time finding an area like that. And yet, finding that area is very important in math and engineering. So what we can do, though, is since I can't get that area exactly underneath the curve, I can approximate the area under the curve. Okay, I can approximate the area under the curve. And so what I do here, and I'll put the A back here for part A, is I'm going to use I want to say it right. I'm going to use right endpoints to determine how high my rectangles are going to be. See, what I want to do is to approximate the area under the curve. I'm gonna take this interval. Okay, hold on. Maybe I'll put it in red. I mean, think about how you would do this. You know, if you didn't know, like if you just had to, hey, you know, find the area underneath the curve, approximate the area underneath the curve. What would you do? Well, you would look at the interval from 0 to 1, and you would say, well, let me draw in some boxes relative to the curve, some rectangles, because I can find the area of rectangles, and then I'll add up the areas of the rectangles. So what I do is from 0 to 1, I divide the interval up into 4 intervals. Now this is because we're going to be using 4 rectangles to approximate the area. Okay, we're going to be using right endpoints. So what I do is I break my interval up from 0 to 1 into 4 subintervals, as you can see here, 4 subintervals. And I'm going to draw a rectangle on each subinterval. So let's go, and again, I'm going to give you time to copy this, but you know, you don't need to copy now because I'm going to give you some time. Just you know, free your mind completely for the discussion here. So okay, my first subinterval goes from 0 to a fourth. There it is, right? 0 to a fourth. Okay, very nice. 0 to a fourth. But so if I wanted to find the area of this rectangle here, well, and I've drawn this rectangle, right? I've drawn this rectangle right here. Now, what's the formula for the area of a rectangle? Who can quickly chat that out to me? I hope you know the formula for the area of the, okay, good everybody. Base times height, width times height. Well, that first blue rectangle that I've drawn, what's the width? What's the width of the rectangle? Good, a fourth. Okay, very good, Nicholas, very good, Yaki. And what does the height appear to be of this blue rectangle? The height appears to be an eighth. Good, good, Joe, good, Zoe. Okay, so, but now the question is, how did I get the height of an eighth? You know what? How am I getting that? Well, in this interval, okay, you have 2 endpoints. You have a 0 on the left, and you have a fourth on the right. You have a left endpoint, which is 0, and 1/4, which is the right endpoint. I'm going to use the value of a fourth to determine how high the rectangle is. So what I do is I draw the rectangle. I want to say this the right way. When x is a fourth, the value of the function at x equals a fourth, which would be 2 times 1/4 squared, which is an eighth, that determines the height of the rectangle. So then the next rectangle goes from a fourth to a half, right? I'll draw on the next rectangle here, and maybe I'll do it with the, I mean, here's the next rectangle. I'll draw it in blue. This will be in the recording. There's the next rectangle. Okay, the next rectangle, its width is also a fourth, right? But the height of the rectangle, I'm going to use the right end point to determine the height. I'm going to use the right end point, which is a half. So the height then is going to be equal to the value of the function when x is a half. And so the value of the function is right there. I'm putting it right, nice big dot. It would be 2 times 1/4 squared. So all the heights of the rectangles, there are 2 other rectangles here. Their heights are determined by the right endpoints in the interval. Just ignore that, please. Okay, one moment. Got to teach here. Okay. So are we okay with, well, and now actually for part A here, when we're trying to approximate, well, the area under the curve, I'm going to add up the area of 4 rectangles, okay? So again, 4 rectangles. The first rectangle has base or width, the width of a fourth, and height of 2 times a fourth squared. So this here is the area of the first rectangle. This here is the area of the second rectangle. Again, the width is a fourth, but the height is 2 times a half squared. Here's the area of the third rectangle, and here's the area of the fourth rectangle. Okay, so I want to like go over A and make sure you're comfortable with A before I move to B, where I use the left end points. Are you okay with what the discussion so far for part A here? Are you okay with the picture and with the R sub 4, the estimate? Oh, Ian says the first height should be 8. It's a very good question. Very good comment, Ian. Very good comment. The first height is an 8th because the first rectangle, yes, the first rectangle has a height of an 8th. So here's the height right here for the first rectangle. Here's the height. What's 1/4 quantity squared? 1/4 quantity squared is a 16th. What's a 16th times 2? What's 2 times a 16th equal to? 1/8. 1/8. So yeah, the first height, the height of the first rectangle is an 8th. Let's look at the second rectangle. The second rectangle has a height of a half, right? Okay, well, the second rectangle, here's its height. 2 times a half squared. Well, a half squared is a half times a half, which is a fourth. 2 times a fourth is a half. So it checks out. The third rectangle has a height of 9/8. Well, let's look at the third rectangle here. Maybe I'll put it in red. The height of the third rectangle is the value of the function when x equals 3/4, right? Well, that's 3/4 quantity squared, which is 9/16. 9/16 times 2, is 18/16. 18/16 simplifies to 9/8. And then finally, the last height here, the last height is 2 times 1 squared. Well, when x equals 1, the height of the rectangle here, that fourth rectangle, is 2 times 1 squared, which is 2. Okay, so Ian, are you, very good question. Ian, are you comfortable? And is everybody comfortable? Okay, good, because you're going to be doing this too. You're going to be doing this too. What I'm doing here is something you're going to be doing in your next homework. Well, Lynn says, is there a reason we would write it out like this instead of just writing 1/4 times 9/8? Well, the reason, what I'm trying to do here is maybe let me see here. Let me just. That's a good question, Lynn. There is a reason we're doing this. So this here is f of a half. This here, this here is f of 3/4. This here is f of 1. And then the first value here, that function there, that was a value of the function f of 1/4. See, the function values at the endpoints determine the heights of the rectangles. So in this picture, I mean, you know, how did I get an 1/8? How did I get a half? How did I get 9/8? How am I getting the values, these values for the heights of the rectangles? It's because I'm evaluating the function at the right endpoints. And so in order to understand this, you know, this is fundamental that we write it this way. Okay, Lynn, are you okay with that? Are you seeing why we do it that way? Okay, good. Well, in class, what we're going to get is then for our estimate of R4, our estimate R4 is going to be 0.9375. That's our approximation using right endpoints to determine the heights of our 4 rectangles. And is this approximation, is this approximation or estimate, would it be an underestimate or an overestimate based on the picture in A? That's right, Nicholas. It would be an overestimate. That's right, Rodrigo. Yeah, there's no question. I mean, we have the area under the curve. The area under the curve, you know, doesn't include this part here. Doesn't include that part. So when you add up the areas of the rectangles, you have area that you don't want. But that's just the way it is when you approximate with rectangles. So R sub 4, okay, R sub 4, we say then overestimates the area A under the graph. So the area A under the graph, when I say area A, I mean like the exact area, So that exact area A under the graph from x equals 0 to x equals 1 would be less than 0.9375. Okay, are there any questions with part A? All right, well then let's look at part B. Part B now, what we're doing is we are using the left endpoints. And you notice how I label my, like in part A, I labeled my endpoints x1, x2, x3, x4. You notice how I label the endpoints x1, x2, x3, x4. I mean, I can do that. I can label those that way. And then the width of each subinterval I call delta x. That triangle there in front of the x is called delta x. Well, you've seen that. You've seen that notation with your differentials, right? But in regards to the area of a rectangle, delta x is the width of the rectangle. And all the rectangles will have the same width for our purposes here. Now in part B, we're going to use the left endpoints, okay, to determine the heights of the rectangles, the left endpoints. So you see the heights of the rectangles. You still have 4 subintervals, right? You still have 4 subintervals here in part B. Okay, you still have 4 subintervals, but the heights of those subintervals are determined by the left endpoint in each subinterval, as opposed to the right endpoint in each subinterval. Okay, so if I wanted to kind of, in part A here, I'd put a, I mean, let me just kind of put, I'm putting nice bold blue dots for the 4 right endpoints in A. And for part B, I'm going to put nice bold blue dots for the 4 left endpoints. And then, of course, the left endpoint approximation using 4 subintervals is found appropriately. It's the area of 4 rectangles. The first rectangle has no area because even though the width of that rectangle is a fourth, the height is 0 because this here is f of 0. Well, I want to be careful. Hold on. Let me put it in black here. This here is f of 0. This here, for the second rectangle, 2 times 1/4 squared, is f of a fourth. Third rectangle is f of a half. The height, 2 times 1/2 squared, is f of a half. And then the last rectangle, 2 times the 3/4 squared, would be f of 3/4. Okay, and then L sub 4 will be equal to 0.4375. Are there any questions up to here? Please let me know if you have any questions. All right. Well, would L sub 4, the approximation for part B, using the left endpoints, would the approximation L sub 4 be an underestimate or an overestimate based on the picture here? Yeah, that's right. So definitely an underestimate. That's right, Nicholas. That's right, Betsua. Because the areas of the rectangles, good, Rodrigo, don't capture these areas here, right? You're missing your, well, and then here, you know, there's it's a big area missing here. So it's an underestimate. So you have to be a little bit careful when you do, you know, like in WebAssign, there will be problems where you have to, you know, answer, is it an underestimate or an overestimate? And when you answer it, you know, you just have to be careful because you only have one chance usually to get that right, you know. And I want you to get it right, okay? So, all right. So let me just see here if there's any questions here. One moment. Okay, John has a very good point. Would we then, so we know that these are crude estimates. And, you know, sometimes what people will do is they'll, you know, like you can average, if you have an overestimate and you have an underestimate, you might try averaging the two estimates, you know, add the two estimates, divide by 2, and that might get you a better approximation, but it still can be somewhat crude. So John's right. If you were to increase the number of rectangles, increase your number of subintervals, the rectangles would more better fit into the under the curve. They would fit better. They would fit better. And I think what I'd like to do is actually we'll move to part C. We will move to part C, but let me actually bring up the ebook here and show you the effect of that. One moment. Now the book works out a similar example, example 2, where their function is f of x equals x squared. But they don't have it isn't 2x squared, it's just f of x equals x squared. I wanted to do something a little different. You know, I wanted to have a 2x squared for our example. But let me show you here. Let me show you here. Hold on. Wait. Just give me a moment. I got to get it here. Okay, so let me bring up the ebook. We'll come back to this. Don't worry. We'll come back. Okay, so this here in figure 8 from the ebook, it goes with example 2. And there again, their function is f of x equals x squared. But you can see in figure 8 here how like they have 10 intervals. They're using right endpoint approximations. Figure 8, the first picture, they use 10 subintervals. So they're adding up the areas of 10 rectangles then. based on the right endpoints of the intervals. In the second picture, they're using 30 rectangles, n equals 30. And then in the third picture in figure 8, they're using 50 rectangles. And you can see the more rectangles that you use, the better you're going to be. The better your estimate's going to be. Well, Ian, Newton, of course, and I'm not an expert on math history, but Newton and Leibniz developed calculus, and certainly, yes, I would say that this is how they started. I mean, I got to be careful because I'm not a historian, but we're actually going to find the exact area underneath our curve, and I would imagine Leibniz and Newton went through the same process that you're learning right now. Yes, I would imagine so. Okay. All right. Well, then let's continue on here with the problem. So, all right. Let me bring up the file here. So we've done part A. We've done part B, and part D we're kind of working out as we go. Now we have to do part C. So in part C, we're going to use our sample points as midpoints. So part C is right here. Again, I've drawn the function f of x equals 2x squared. We are trying to estimate, we want to estimate the area under that curve from x equals, one moment here, from x equals 0 to 4. Let me screw this up. There we go. And then I screw it up, and then I have to unscrew it up, right? Okay, so now what I do is, like the first interval goes from 0 to a fourth, first subinterval, right? There it is. But I'm going to use the midpoint between 0 and a fourth. The midpoint is that x1 there. Now, incidentally, what's the value of x1? What's this value equal to? It's halfway between 0 and a fourth. An eighth. Okay. Good, Nicholas. And, okay, well, so the function height then, the height of that rectangle, okay, the height of that rectangle right here is determined by the function evaluated at x equals an eighth. Okay. So this here's the area of the first rectangle. Now, the second rectangle, subinterval goes from a fourth to a half. What's the midpoint between a fourth and a half? Well, let me ask you this. How can you find x2? You have a fourth on the left. On that interval, you have a value of a fourth on the left, a half on the right. So Ian says 3/8, and that's right. And how did you get 3/8, Ian? There are really two ways to do it. Okay, right. 4/8 plus 2/8. and divide by 2. Very good. So hold on here. The 1/4 here, the 1/4 is equal to 2/8. The 1/2 is equal to 4/8. So if you take 2/8 and 4/8, you get 6/8. Divide 6/8 by 2, and that'll get you 3/8. And so the height of the second rectangle is f of 3/8. And you notice on the y-axis, I've not put 3/8 here. Hold on. Man, 8s are not easy to make. Okay, so I've not like written down on the axis like what that value is, as like with A and B, because it's harder, but it's okay. And I think you know that x sub 3 would be 5/8. And incidentally, you can take on your calculator, you can take 1/2 plus 3/4 and divide that by 2, divide that sum by 2, and then go to math frac on your calculator and turn that decimal into a fraction. Okay, how many know about math frac on the TI 84, 83 calculator? There's a math button on the left of the calculator, and when you hit math, there's a feature, it's in the first one actually, FARC, math. You hit frac and it converts decimals to fractions. I don't know if you've seen that. I imagine you all have, or many of you. Sure. Well, all right. So Joe, it's the first time. All right. Ian's seeing it. Sebastian's seeing it. Okay. Okay. And then the x sub 4, Rodrigo has. Wonderful. That's 7/8. And so there's your f of 7/8. So what you're doing is you're taking your delta x and you're multiplying delta x by the height of each rectangle. And I'm putting in this notation because it's going to be helpful for the next example that we're going to do. If you add all this up, you're going to get 0.6525. Okay, let me just give you a moment in case you're copying a few things down here. I want to make sure I'm pacing myself right. So I'll give you a moment here. All right, so let me ask you this. Here's our midpoint approximation, 0.65625. Based on the picture up here, do you feel, I mean, what do you think's the best, what approximation does the best job? Would it be, do you think L sub 4, M sub 4, or R sub 4? Which approximation seems to work best here? I'm getting comments about the midpoint, and you're right. You can see graphically that the midpoint rule gives the best approximation to the area under this curve, or I should say the midpoint approximation, where you use the midpoints as your sample points. Okay, well, let me ask you this. Do you think the midpoint approximation then, M sub 4, would it underestimate the actual area A or overestimate the actual area A? Take a moment to think. So the question is, would M4, so we agree M4 is the best approximation of the three approximations to the area, to the actual area A underneath this curve, from x equals 0 to x equals 1. But my question is, would, you know, like we learned that the L sub 4 approximation underestimated the area A under the curve. The R sub 4 approximation overestimated the area A under the curve. I'm wondering about the M sub 4 approximation. Would this approximation overestimate or underestimate the area under the curve? That's my question. And to give you a little hint, take a look at like, for instance, this third rectangle. Okay, the third rectangle, do we want that area? Well, we're going to see, Sebastian, and you might be right. We're going to see. This area here, do we want that area that the box has, that red area there? Do we want that red area? No, we don't want that red area. Good. Good, Lynn. Good, Rodrigo. Good, John. All right. What about this blue area here for the, you know, where we use the third rectangle? That area, do we want that area? Yeah, we want that area, but the rectangle doesn't get that area. That's right, Trevor. So which is more, the blue area or the red area? Which is more? The red area is the area that's in the rectangle, that's contained in the rectangle. The blue area is, okay, so the blue area is more than the red area. Okay, blue area is more than the red area. This is a concave up function. Okay, f of x equals 2x squared is a concave up function. Okay, so so what's happening then is that M4 underestimates the area under the graph. Okay, so 0.65625 here is an underestimate of the true area under the graph, because if for every rectangle there's red area that is in our approximation, in our estimate, but blue area that we didn't get, and the blue area outweighs the red area. So you're gonna be underestimate. The balance will be that you have an underestimate. Okay. Are there any questions on this? Any questions at all? Let's see. Nicholas says, can you take the area over the curve? Can you take the area over the curve and put it into the missing area under the curve? No, no, you can't. You can't do that. You have to work with what you have, Nicholas. I mean, I'm not saying there aren't things that you could do, but really, I want to keep things simple. All I'm interested in doing is adding up areas of rectangles because I know how to get areas of rectangles. Anything else might be kind of tricky to do. Okay, all right. Are there any other good questions? All right. Well, how many of you would love to know how to find the exact area underneath the curve? The actual exact true area underneath the curve. Yeah, I'm going to show you how to do that. I'm going to show you how to do that. You know, to find the exact area underneath the curve. Okay. All right. Well, then let's go to the next example. May I go to the next example? Are we good? All right. Okay. Very good. Then here we go to the next example. Now what we want to do is we want to find the exact true area under the graph of this function f of x equals 2x squared from x equals 0 to 1. To do it, we are going to need a formula. Okay, this is a formula that can be found by what's called induction. How many have heard of induction? Maybe you've seen it. It used to be like when I taught high school many years ago, and we actually taught induction in our pre-calculus class. But I don't know if you've heard of it. But this formula here, they actually, let me just see. If you wanted to see a proof of this formula, in the appendix, Appendix F, the formula, I believe, is proven there. Yeah, it is proven in Appendix F, Example 5, in Appendix F. So if you're interested in seeing how they get that formula, that's fine. All right, let me give you a moment to copy this example down. Okay, everybody. So, all right. Let's go ahead and look at this problem step by step here. All right. So, what we're going to do in our solution here is we're going to be a little more general here. So, this width of the subinterval, delta x, is, as you know from the previous example, it's the width of the subintervals. Every subinterval is going to have the same width. Okay, and we want to find the width of the subinterval, but we kind of like to do it. Easily. So all you need to do is the b minus a over n. Okay, n is your number of subintervals, and the value of a is like in your interval, it's the left endpoint, and the value of b is the right endpoint of the interval. So the situation is you have area here, you have some function f of x, and the leftmost value of the function, the value of the function starts at x equals a and ends at x equals b. Okay, that's how you determine. That's how a and b are defined. Okay, that's how a and b are defined. Okay, and then you're looking to find the area under the curve. Okay, so okay, so now for our problem, a was equal to 0, okay, and b is equal to 1. So 1 minus 0 over n is 1 over n. So the width of your subinterval is a function of n. It depends how many subintervals you're going to take, n subintervals. Okay, and what we're going to do here to find the exact area under the graph is we're going to use right endpoints. We're going to use right endpoints. And so like in the last example, we had we had 4 subintervals, and we had x1, x2, x3, and x4. So 4 subintervals means you're going to have x1, x2, x3, x4. Okay, no problem there. Well, if we have n subintervals, we're going to have then x1, x2, x3, all the way up to xn. Okay, and the way you can get the values of your x's, x1, x2, x3, all the way up to xn, is you take the value of a. Now this is for the right, using right endpoints, but you take the value of a. In our case, a was equal to 0. Okay, and you add delta x to it. Add 1 delta x, and that's going to get you x1. Well, 0 plus 1 over n is 1 over n. Now for x sub 2, the second value, where which is going to that x value, the function evaluated at that x value would determine the height of the second rectangle. X sub the x sub 2 value would be a plus 2 times delta x. That's going to get you 2 over n. The third x value would be equal to a plus 3 times delta x. That's going to get you 3 over n. And this is consistent. If you look at the last example, if you look at the values of x1, x2, x3, x4, you can use this approach here that I'm showing you. And it really is the approach. I'm just generalizing the approach here. Okay, x sub I then would be 0 plus I times delta x. That would then be equal to I over n. And finally, x sub n would be 0 plus n times delta x. But n times 1 over n is just 1. So that makes sense. Your right endpoint is going to be the last, the highest value of x. X goes from 0 to 1, so 1 is the last value of x for your interval, and you have to, x sub n would have to equal that last value. Okay, so now what we need, well, first of all, before I go forward, is there any question on this process here that I'm showing you? Do you have any questions at all on that? Okay, Betsu is good. Okay, Rodrigo's good, John's good. Okay. Well, now what I'm going to do is I'm going to give a formula. The B and the A, Sebastian, the B and the A come from when we said we wanted to find the exact area under the graph from x equals 0 to x equals 1. X equals 0 was the value of A. X equals 1 was the value of B. So now, like for instance, let's say they said find the area where from x equals 2 to x equals 5. Well, in that case, x equals 2. 2 would be equal to A, your starting value, and 5, the ending value, would be your B. Okay, so that's how you get A and B. All right, very good, very good. Well, now what we're going to do, we realize that to approximate the area under the curve, we have to add up n rectangles. We know that the area of a rectangle, of the ith rectangle, is the width of the ith rectangle, and we know that we know that to find the area of the ith rectangle, we have to take its width and multiply it by its height. Well, every rectangle has a width of 1 over n. That's your delta x. Okay, that's your delta x. Let's try to make this look good. I want to make everything look good. Again, I'll think a lot better with the mouse now. Hey, maybe for the holidays, I'll get myself a stylus. Okay. All right, Nicholas likes that. Very good. But I'm doing okay with the pen. I'm doing okay with the mouse. Now this 2 times I over n squared, that's just equal to f of what? What is 2 times the quantity I over n squared? That's f of what? Need to put something in here. Give you a little hint. 2 times the quantity I over n squared is the same. That is the height of the ith rectangle. The height of the ith rectangle comes from evaluating the function at x sub well, not x sub n, but x sub all right. It would be we're close. John's the closest. Some good efforts here. Kelvin has it perfect. F of x sub I. F of x sub I. And we're adding up these rectangles. How many of them? There are n rectangles. So you started at I equals 1, the first rectangle, all the way up to n. How many have seen summations in pre-calculus? I think you would have seen them there. Okay, Nicholas has seen them, and okay, this means this is just the summations. It means add up all the rectangles, but you're letting every rectangle has an I in it in the formula, so you're letting I go from 1 to n. Okay, it's just a brief way of saying add up these n rectangles, add up the areas of these n rectangles. Okay, and let me just go back for a moment to the previous problem real quick. So, you know, like for r sub 4, when we had 2 times 1 squared, that was f of a fourth, but that was f of x sub 1, right? And then 2 times a half squared, that was f of a half. Evaluate the function when x equals a half, but you know, a half is x2, right? So that's f of x sub 2. 2 times 3 to the fourth squared, that is when x was 3/4, but that's x sub 3 then. So I want to make sure that you're getting the connection here, because you're about to learn something really amazing. And then 2 times 1 squared is f of x4. Okay, and then of course all the 1/4, every one of them stands for delta x. Every one of them. So what I'm showing you in this second example is it's nothing different than what you did in the first example. Okay, you're when you add up the area, when you have the area of a rectangle, it's always going to be delta x times a function evaluated at some x value. And so hopefully then this here Makes some sense. Was that helpful to sort of go back? And I'm trying to make sure, I'm trying to tie things in for you, you know? All right. Are there any questions before we move on? All right, well, now what are we going to do with this? What are we going to do with this formula, this right endpoint approximation, R sub n? Well, on the next page, I rewrite the formula. Okay, I rewrite it. And I'm going to try to, simplify things a little bit. So I square the I over n quantity squared is I squared over n squared. Okay, so the formula, the right endpoint approximation R sub n, can be written this way. And then I have an n and an n squared here in the denominator. I can just write that as n cubed. And so I'm going to have the sum where I goes from 1 to n of 2 over n cubed times I squared. But 2 over n cubed, in regards to the summation, is a constant. The summation goes from I equals 1 to n. Okay, but it's not I mean, 2 over n cubed is treated as a constant then. Okay, so you can bring 2 over n cubed out in front of the summation. But the summation of I squared, where I goes from 1 to n, is just 1 squared plus 2 squared plus 3 squared all the way up to n squared. Okay. 1 squared is when I equals 1. 2 squared is when I equals 2. 3 squared is when I equals 3. And I keeps increasing until it stops at I equals n. But we just learned that 1 squared plus 2 squared plus 3 squared plus so forth up to plus n squared, that sum equals n times n plus 1 times 2n plus 1 over 6. And that would have to be given to you in any problem that where you're, I mean, we're going to find the exact area in section 5.1 for this problem. So we need to have that formula. So what I'm trying to do is rewrite my R sub n formula. I mean, the right endpoint approximation R sub n ultimately is a function of n, right? And now what I've done is I've rewritten R sub n as a function of n alone by evaluating the summation using the formula. Okay, let me give you a moment to think for a moment before we go to the next page. Okay, and so what I do is the entire expression here for R sub n, guess I'll have to erase this. The entire expression for on the right, of course, for R sub n, I just rewrite it in this nice way. You know, the n cubed is n times n times n, so I put the n's here, and underneath, you know, the n plus 1, and the 2n plus 1. All right. Are there any questions up to here? Are we good? Okay. Well, now what we want to do is we want to, well, we know that this right endpoint approximation R sub n is going to get better and better as we increase the number of subintervals, right? It's going to get better and better. And so what if we were to take the limit of this right endpoint approximation as n goes to infinity? If we did that, would we get the exact area under the graph? If we let the number of subintervals go to infinity, would the limit of that, would the limit then of our right endpoint approximation R sub n, would the limit of that have to be equal to the exact area A under the curve from x equals 0 to x equals 1? Yeah, well, Ian, actually, we can do, you're saying probably, it's actually a yes. But I like probably. Ian just doesn't want to take it for granted. I understand that. It absolutely will. So the area actually is a limit. The exact area under the graph is going to be the limit of that right endpoint approximation as n goes to infinity. It has to be. It has to be, because remember, you had said, you intuitively understood that the more subintervals you take, the better your approximation is going to be, right? Remember, one moment. Let me one moment here. One moment. Let me bring this up, because I want to make sure that this is like a really important moment for you. You're learning something really great here today, right? We agree that the more subintervals you take, based on figure 8 here, you can see the more subintervals going from n equals 10 subintervals to n equals 30 subintervals in the second picture, to n equals 50 subintervals in the third picture. You can see the approximation just gets better and better. Okay, and you know, here in figure 9, they have here on the right picture, they have 50 subintervals, and it's getting where adding up the areas of the rectangles is basically indistinguishable, that area from the area under the curve. So there's no question that adding up the areas, letting n go to infinity, taking more and more subintervals, and letting the number of subintervals approach infinity, there's no question that then the area under the graph will be exactly equal to that limit. And so if you take the limit then of a third times 1 plus 1 over n, hold on here, find it, times 2 plus 1 over n. That's going to be a third times 1 times 2, and you get 2/3. And that, everybody, is the exact area. That is the, I mean, that's not an approximation. Area equals 2/3. That is the exact area underneath the function f of x equals, this should be 2x squared, by the way, not x squared, it's 2x squared. Let me fix that. Oh, well, we don't really, hold on, Sebastian, one moment. Let me put in my 2x squared here. That's our function, right? Well, how do we know it's true, Sebastian? Intuitively, don't you feel it's true based on our based on what we just worked through? I mean, we didn't use any special, I guess I want to be, I see. So Sebastian's sort of like saying, how could you, I mean, it isn't like the area of the area of a rectangle or a circle, you know, we can get those using other methods. Here we're using a limit method to get the area, but that is, it's an approach that you've not seen before, Sebastian and everybody, but it is legitimate. It is legitimate, because we agreed on the previous page. We agreed on that. Let me ask you this, Sebastian, and I'm going to do this with you because I think other people might help other people. Sebastian, are you okay that the right endpoint approximation equals 1/3 times 1 plus 1 over n plus times 2 plus 1 over n? Are you okay with this last circled statement here? You're good with that part, all right? And Sebastian, do you agree that as n gets large, that this right endpoint approximation is going to better and better approximate the area under the curve? Okay, so what's the best we can do? What's the best we can do in terms of number of subintervals? Is 1,000 subintervals the best we can do for n? N equals 1,000? No. What's better than 1,000 subintervals? That's right, Nicholas. What's better? Okay. So Nicholas says like a quadrillion, a billion, and then of course infinity is the best you can do. So you take then the limit of your right endpoint approximation by letting n go to infinity. Well, there's no such thing, Nicholas, as infinity plus 1. The infinity plus 1 would be infinity. Now, there are different types of infinity, but you're going to have to take a course in topology to learn that. Well, Ian, that's infinity. Infinity plus 2 billion. Infinity, you know, is like infinity. And so, yeah, this area here, this shaded area, all this shaded area, infinity minus 1, Joe, is infinity. Yeah, because infinity keeps going, keeps getting bigger and bigger and bigger, right? Never ends. So, infinity never ends. All right. Okay, very good. Well, now you have found your first area underneath the curve. And again, you know, the curve, I had written it before, but the curve is 2x squared, right? So that you found your first integral. You have found your first integral, definite integral. Okay, that's what you found. A definite integral is area underneath the curve. I hear you, Sebastian. That's the beauty. That's the beauty of things. All right, and I want to show you one more example from the textbook. You'll be able to have some class time to work on section 5.1. Well, Ian, it's 2x squared though. Remember, it's our function was 2x squared, not x squared. If you had x squared from 0 to 1, I see what Ian's saying. Ian's saying, what if our function were just x squared? Would then the area be cut in half? Yes, it would. Excellent. The area underneath the function f of x equals x squared from 0 to 1, the area under that curve is equal to 1/3. That's exactly right. And that's what they confirm in the book in example 2. Very good. Very good. So all this shaded area here is equal to 2/3. Okay. All right. Are there any other good questions? All right, then let me go ahead and go to the textbook here. I'll bring up the textbook. So this is what's called the area problem that we looked at. Okay, we looked at what's called they call it the area problem, the problem of finding areas under a curve. But there's another problem called the distance problem. I don't like to get too heavy into terminology, but they also show you some of the terminology that we talked about in the problem. I wanted to kind of keep everything together, you know. But the distance problem. Okay, so this is a problem actually that is similar to the area problem. In example 4, they say, suppose that the odometer on our car, this is from our ebook, suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. Okay, and so what you do is suppose you take speedometer readings every 5 seconds and record them in the following table. Okay, so what you've done is every 5 seconds you've taken a speedometer reading, which gives you the velocity. So at time equals 0 seconds, the velocity is 17 miles per hour. When the time is 5 seconds, the velocity is 21 miles per hour. Okay, but then they say, all right, in order to have time and velocity in consistent units, let's convert velocity readings to feet per second. So what they're doing now is they're saying, okay, at starting time, your velocity is 25 feet per second. So, okay, and then after 5 seconds, your velocity increases to 31 feet per second, and so forth. So they're converting they're converting the table here into a new table where your units are going to be in feet per second. And they make a comment here. During the first 5 seconds, you know, if you have a short interval, 5 seconds, the velocity doesn't change much. Okay, so we can estimate the distance traveled during the first 5 seconds by assuming that the velocity is constant. Okay, and so if you were to then take the velocity of 25 feet per second, okay, over the first 5 seconds, and assume that velocity is constant, how would you get the distance you've traveled? You take 25 feet per second and multiply it by 5 seconds. And that will get you 125 feet. Okay, so remember, position, if I want to say this the right way, velocity is the derivative of position, but the antiderivative of if you take the derivative of position, you get velocity. But if you do the antiderivative of velocity, you get position. Okay, and what they're doing here is they're working with velocity and going back to get distance, or in this case, position. So now for the second, I want to say this the right way. Hold on here now. Okay, so starting at, I want to be a little bit careful here. So at 5 seconds, the velocity reading is 31 feet per second. At 10 seconds, the velocity reading is 35 feet per second. So during the second time interval, which would be from 5 to 10 seconds, they're going to assume the velocity is approximately constant, and they're going to use the left endpoint of when t equals 5 seconds. So they're using in this, like for the first estimate of 125 feet, they could have used 0 seconds or 5 seconds for that time interval, but they used 0 seconds. They used 25 feet per second, that velocity when time was 0 seconds, to get the distance. They're doing the same thing here. Now we're going, the second time interval goes from 5 seconds to 10 seconds, and they're using the velocity at 5 seconds, which is 31 feet per second, and multiplying that by 5 seconds to get the second distance. Okay, and so it's like they're using a left endpoint approximation, and if they continue doing it, they're going to estimate that the total distance traveled over the 30 seconds is 1,135 feet. Okay, are there any questions on that? All right. Well, then they comment that they could have used the velocity at the end of each time period instead. If they did it at the end of each time period, that would be like the right endpoint approximation, and you would get a different estimate. Okay. And they note that if you want a more accurate estimate, you could take velocity readings more frequently, like every 2 seconds or every 1 second. So there's an analogous, this analyzation of finding the distance you traveled based on velocity readings is analogous to the area problem that we had, that we just looked at. That's what I wanted to mention here. Are there any questions on this example 4? Are there any questions on that? Okay, Nicholas is good. Okay, good. All right, then let me stop the recording.